So to keep the continuity, we will go to the next step of how weather to climate change happens. As you already probably realized, weather to climate, the definition is not rock solid in the sense when does weather become climate. Is it after 10 years, 20 years, 30 years? Some time scale has to be decided, and then it's even more challenging to say when it becomes climate change, because it may be changing for 10 years and then coming back to as it was before, in which case it would be called decadal change. It could go away from what you are expecting for a couple of decades, 3 decades, and then come back, in which case we will call it multi-decadal change. And then we are now constantly talking about climate change, anthropogenic change. Oftentimes we are comparing that time scale to what things were like, let's say at the beginning of the Industrial Revolution and where we are headed now. So it is the trend, how things are changing over time, that we are most interested in. So looking here at annual average temperature changes in Salem, Oregon, you are now looking at a much longer time scale going from 1895 to 2020. So the book is quite up to date, and they will keep updating it, so you can always revisit the book. As I'm recording, I will use the figures that are available. Obviously you can always keep looking at the newer data. So typically we look at anomalies in this case. Anomaly is exactly what intuitively you think of. It is a deviation from what you expect. If you expect November 16 to be about 50 to 55 degrees and it is 40 to 45 or 65 to 70 degrees, you say it's anomalously cold or anomalously warm. So anomalies are compared to some baseline. So here the average is being compared to 1903 to 2000 to 2000. So the mean over that period is 53.2 degree Fahrenheit here. So that line has been drawn across the whole period, and you can see that the temperatures are somewhat below that average during the period of 1895 to about, let's say, 1930 or so. With some jump here, and then it remains above that, and then it has gone way above that over the more recent decades. So you can take the change, so you can take temperature here in let's say here in 2020 and subtract the temperature from 1895 and divide by the time period of whatever number of years here. That gives you the so-called linear trend. So that is computed here to be 0.2 degree Fahrenheit per decade. So the warming over Salem, Oregon has been 0.2 degree Fahrenheit per decade, but you can see that the temperature doesn't increase monotonically. It goes up and down. Why? Because the natural seasonal changes, year-to-year changes are still happening, but the entire baseline is slowly moving up. Okay, so there is still warming in the summer and cooling in the winter, but you can see that the warmest temperatures in summer have gone up and the minimum temperatures in the winter have gone up. So the maximum, minimum, average temperatures are typically going up to give you a trend over this time. Do we call it climate change? Typically yes. This is multiple generations, so we have to call it climate change. You can also look at averaged over the state of Oregon temperature fluctuations. So you can see the different baselines are used here. Trend for 1895 to 2016, 1901 to 2000, and average temperature. So if you look at the long term, the average has gone up here. The mean for this period is 46.5 degrees Fahrenheit, and the average temperature for each year is shown here in this as this is now not a deviation. I should have been careful about that. Okay, so here are total temperatures as well. So you can see again that the maximum temperatures have inched up, and this is now averaged over the whole state. So you keep doing this. When you want to do global warming, you want to average over the whole globe. Okay, so here are the contiguous United States average temperature, the January to December, again looking at about 1895 to 2016. Again you have a trend, and you have the average, which is 52.02 for the entire US compared to 46.5 for Oregon, and 53.2 for Salem, Oregon. Okay, so it depends on what you are averaging, but you can see that below the long-term average here, about the long-term average here, about the long-term average, and above the long-term average here. Now you take it to global land temperature anomalies. Again, similar period. So there is a trend here. For the long term, 1880 to 2016, the global land temperature trend is 0.1 degrees centigrade per decade. The land was cooler than the long-term average before about 1930. It started to oscillate around the long-term mean up to about the 1970s, and then it has stayed above. It still goes up and down, but you can see that it is warming. Now we are looking at anomalies. Here we looked at total temperatures, whereas here we are looking at anomalies, because on a global scale it is better to look at the average temperature and deviations from it. Okay, so this is the average over a certain base period of 1901 to 2000, and deviations from that. So cooler than this average before this period, around it, and then above it. Okay, and there are other ways to look at it. Even though it is going up and down every year, if you look each decade since the 1980s, each decade has been warmer than the previous decade. So again, averaging over a decade shows you that the warming is real and serious. If you look at global ocean temperature, it is slightly different than the land temperature, and you can see the trend is smaller because ocean is deep, has a high heat capacity. We will see later that it takes up almost 93% of the excess energy that human beings are trapping by increasing the greenhouse gases. Again, we're getting a little bit ahead, but just keep that number in mind. So the warming is, you can see here, it is more than 2 degrees Fahrenheit here. It is less than 2 degrees Fahrenheit here. You can also see in anomaly degree centigrade. So ocean warms less and slower, but it keeps all the energy. It can keep tremendous amount of energy. So now you can do global land and ocean and get a slightly higher number, 0.07 degrees C per decade, which is smaller than just the land and greater than just the ocean. Okay, so these are how you keep adding more and more time scales and keep understanding more and more about how weather becomes climate. Climate can change, and then we have to understand why climate changes and what the consequences are. So in the weather, we looked at Corvallis temperature change, precipitation happening in winter months. Now we said Corvallis temperature is warming, minimum and maximum temperatures are warming. What's happening to the precipitation? It's not so directly relatable, because precipitation, as we saw, is a very noisy thing, unlike temperature. You can think of it this way: if you are sitting in Corvallis or in Mumbai, think of temperature over Corvallis. It will be similar over large area of Corvallis or even neighboring towns. Same for Mumbai. But It could be snowing or raining only in part of Corvallis. The other regions of other parts of Corvallis may be dry. The same for Mumbai. So rainfall is very local. Temperature is got a larger scale over which it remains the same. So you can think of it as a popcorn kettle. A kettle is getting warmed. It probably has the same temperature over the whole kettle. Metal has low heat capacity, warms fast, and heat diffuses quickly, conducts quickly, and gives you basically very uniform temperature. The kernels in the kettle, though, they pop randomly here and there, right? So precipitation is like that. Land is warming or the ocean is warming, and convection or processes that create rainfall are just popping like popcorns. There are many processes, details, depends on how the rain is being created, whether it's because the air is rising over a mountain and expanding and raining, or whether it's just heating quickly like in the tropics on land, or over the ocean where the moisture is infinite, or whether there is a front coming in from somewhere and meeting cold air, or a cold air coming and meeting the warm air, and so on and so forth. Many details, but what is true most of the time is that rainfall is always got a much smaller spatial scale and can happen very fast, and so also faster in time scale than temperature scales that you typically find. Okay, so those are the things you have to just get oriented with in this first chapter. In the second chapter, we will look at the typical data we collect, and then we will look at some of the paleo data we collect, and then we will begin to get into more juicy parts of climate science. Okay.